Hello everyone. So here we can list out the base SI units. So why I am putting a line here is this is the first three things that usually you learn in mechanics. So all these three. And therefore you are already familiar with this. So now once you finish your mechanics and when you are going to learn thermodynamics, for example, usually that is how the courses are organized, right? After the mechanics you study the thermodynamics. You only these three of them are not sufficient. You need something extra. So the one that is extra required is the Kelvin, the unit of temperature, which is a capital K, followed by the number of moles, because you have to measure the number of mole in an ideal gas or whatever it is for describing a thermodynamic phenomena. And therefore, if you are going to say that these are the additional units that are required for the thermodynamical situation, then the corresponding symbols are, you may not be familiar. So the symbol for the thermodynamic temperature is theta. So usually theta is written with this is a capital theta. Now you see that this is a small letter. So this is small letter theta. Capital letter theta means a proper circle should be there and then a horizontal line like this. So this is caps letter and this is the lower case or the small letter theta. So capital letter theta is used for the dimensions. Capital K is used for the symbol. And for the case of the mole, you have to use a capital N. So N is for the number of moles. So you have to write this for the dimensions, and MOL you have to write for the units. So these things are generally used in thermodynamics in addition to the mechanical. It is not that you should remember one thing, that by the word thermodynamics you should not think that the mechanics units are removed and only these two are. It is not so. Mechanics are the base units that are required. Plus means in addition to that, anything else you need has to be added to describe thermodynamic phenomena. So that is the meaning of that. So these are the only two additional units that are required for thermodynamics. Anyway, you have studied thermodynamics already in the last semester, I believe. Only thing is, I am interested to explain that the dimensions you may not be familiar. You are already familiar with Kelvin and mole. So let us have a formal way of writing everything in one place, because there are only 7 of them, not a big number. So only 7 of them are there. As you can see that already 3 plus 2, 5 of them are over. So that means your mechanics and thermodynamical systems can be explained by this. And now you come for the electromagnetism. And for that, how many of them are required? Surprisingly, only one is required. You don't need more than that. So simply you need ampere. That means the measurement of current that is done in the units of ampere. So we write capital A. Okay, we don't write small AMP. There is no need to write like this. But once things are clear, we can use only the capital A for the ampere. Only you write the capital A, and that's what I am written here. But however, the symbol for the dimension is not A, so you have to use a capital I. So I for the current that you will be using. So in the square bracket, now this one corresponds to the square bracket of I. It is very similar to saying that MLT. So similar to writing MLT, now you have to add I here. That is the meaning of the second column in this second column, whatever I am writing. So that should be combined whenever you are writing the dimensions. Okay, only one is enough now. And with this single unit, the entire electromagnetism can be described. And once again, it is not the single alone, it is in combination with the previous one, because you already have the base units for the mechanics, the base unit for the thermodynamics. So anything extra required only we are adding. So only ampere is required, and once you have the ampere with the previously defined base SI units, everything in the electromagnetism can be described. So that is the interesting point. But however, for the sake of completeness, if you want to study the optics, for example, you require one more unit in order to measure the light intensity. You have to talk about how much of, for example, how much sunlight you are receiving on the earth. I want to measure it. So for such kind of studies, you need a unit what is known as a candela. So candela is represented by CD, and then the symbol is capital J. So this J is really somewhat a different symbol, but that is what is recommended by the SI system. So with this, if you count how many of them are there, you see that 1 2 3 4 5 6 7. So there are only 7 units are there. 7. Okay, this portion I will erase so that so only with this 7 you can do everything else in the physics. Not only in electrodynamics, you can study the entire physical phenomena using these 7 base system. So this is the first point that is to be noted. It's very important. It may look very simple also, so that's why I'm once again telling, just because certain things look very simple, you should not think that it is a thing that can be neglected. Okay, it is not so. They are very important and they are very fundamental, and therefore it is necessary to know, and that too you are taking a very first course on electromagnetism. So this is a good starting point or a good opportunity to learn how the derived first of all, what are the derived units, and then how to list them in terms of base units. So quickly we will see now, how do you represent any physical quantity in terms of base unit? So what is the meaning of the statement that we are saying, expressing in terms of, what do you mean by that? So that I will show here. For example, you take any physical quantity. I will not write the name of a quantity, rather than I will say that some physical quantity. So I will write that phy for physical quantity, I will write qty. Any physical quantity. I want to find out the dimensions of the physical quantity. So symbolically we put it in a square bracket, and then we'll say that it goes like that, is this particular physical quantity is equivalent to. So this kind of a symbol, tilde symbol that I have put, is equivalent to. That means it can be equivalently expressed in terms of, that is the meaning. This particular tilde symbol means that it can be equivalently expressed in terms of. Then in terms of what are you going to express? I'm going to express in one of these base units. That means one of these 7. Some of them may not be there. In that case, automatically the power will be 0. If something to the power 0 is there, you get 1. So that means multiplication by 1 will not be visible. So you get it appears as if the particular quantity is removed. Did you understand what I mean to say? I mean to say that if there is a mass, length and time, for example, if one of the power is 0, for example L to the power 0 is there, then if you simplify, I'll get m into L to the power 0 is 1, then I get a t. So it appears as if L is missing. That is the meaning of that. So that means you can always bring all the 7 into picture, but when some of them are absent, it means its power is 0. That's what we are trying to say, that every physical quantity, not necessarily in electromagnetism, it can be any physical quantity, can be written like this. Can be written as, you write mass to the power something. So okay, we can write down to the power also. Then after that you have the length, so to the power something. So we see another number. Something means another number. The number can be a fractional value, it can be an integer value, it can be positive value, it can be negative value, and 0 also. Everything is possible. Then L, then you have a t. So time to the power another fraction. Then you have the temperature, so that means you have to write down the capital theta, and then to the power the next letter, let us say d. Then after that the number of moles, n to the power e. Then you have the current. So for current we have to write capital I, then to the power some other number, let us say f. And finally we have the candela, which has somewhat different symbol j, and then to the power g. And that's all. So this is the meaning that I am trying to say. The meaning, or what I am trying to explain to you, is that anything that you are going to have like this, any physical quantity can be expressed like this. Okay, this is the important conclusion. It is like one equation. So every physical quantity can be expressed like this, where you have to find, this has to be found out by suitable analysis, in which case you have to find out the values for a, b, c, d, etc. up to g. All these numbers you have to find out. Once you find the numbers, yeah, is it correct? Yeah, that's correct. A, B, C, D up to G only. Yeah, once you find all the numbers A to G, your calculation is over. That means you really found out how to express. So this is the overall, that means the whole thing that I wanted to tell you in this class is now contained in this line. So this line has everything what I am trying to explain. But however, in order to demonstrate in a more practical way to understand something, we will consider an example so that you will be knowing how to determine the constants ABCD. So the first thing that we can consider in the case of the electromagnetic unit, so let me write down the title. So if we try to find out what are the physical quantities that are used in the electromagnetism. Now how do you know means you already studied the electromagnetism introduction in the school level. So you know that you have to use some potential difference. You are using some circuit. So there is a current flowing in that. You know something about capacitor. I mean that you know that there exists capacitor to store the charges, and you also know that the units are farads. So something like this you already know. So by that and by this way, you already have some idea about the name of the physical quantities used in the electromagnetism. So if you can list out them here, you will surprisingly see that there are only a few are there, and then you can always decompose as and when required. It is not that every time you do this decomposition in terms of the base SI unit, but it is only for understanding purpose that you do. Every time we will not be doing. Every time there is no need to do this. You can keep the derived unit as such. That means in the case of magnetic field, you can use it as a Tesla. No need to decompose. Okay, so this is for understanding purpose. No, otherwise you do not know what do you mean by Tesla. You have to simply memorize, that's all. How the Tesla is related to the base SI unit, that clarity will come if you do this particular homework. That is exactly we are now doing. So let us see whether a very large number of physical quantities are there, and is it really difficult to list out here, or that there are only a few. So if you list out here, you will see that there are a very few of them are required. So the first one that you will be using frequently in the case of the electromagnetism, the first one that comes into your mind is the Coulomb or the charge. So the first and foremost physical quantity that comes into your mind is the charge, which is expressed in coulombs. The reason why it comes into the first place is this is how the electrostatics is started with the Coulomb's law, and the difficulties in understanding what is Coulomb we have seen in the previous few lectures, and people started with the stat Coulomb definition, and then in the SI system people are studying to understand the Coulomb, and therefore this is the first thing that requires its definition. And the problem got clearly resolved in as per the new definition of the charge in terms of Coulomb. So how it is done is we have a defining equation. So let me therefore write the defining equation later. We will go to that later. As I already told, let us first list out this, then we can go to the definition. So the first one is charge, which is clear to you. The second one is once you have the electrostatics is over, then the Biot-Savart law or the Ampere has given the expression for the current carrying conductor, which means there is a current. So you understand that Biot-Savart law as experiment involved a current carrying wire means, what do you understand? It means that a current is flowing in the wire. And what is the meaning of that? That means there is a potential difference between the 2 points in the wire, otherwise current will not flow. So that clearly tells you that you need something called a potential difference. So I will simply write PD here. So hopefully you can follow this easily. PD for the potential difference, and you measure it in volts. So we need, what is this? So it is very clear that we need these things as we go along based on the definitions. And then the third one, once you have the charge and the potential difference, you can do something like what I mean by saying is that if there is a charge that is available with you, and you also have a potential difference available with you, okay, so then what you can do, you already know with these two quantities you can find something, and that is exactly a capacitor. Okay, a capacitor, you can manipulate these two values, and then if you manipulate you can get something, and that is called a capacitance. So we can measure this in farads, which means that it is not something new. As you can see that this is coming from the charge and the voltage, and from where the voltage came from the this particular charge q. And if you ask the question where is charge, it is there in the electron. So it is not, it is something that you didn't do anything. Okay, the most important point that you have to remember is electron is possessing a charge, and that's all. It is by nature. Somebody did not attach a charge to that. Okay, so having a charge for an electron is an intrinsic quantity. So this term is very important. There are two things are there. One is known as the intrinsic. The other one is known as the extrinsic. So intrinsic property, either you can say quantity or say property. Let me write a property here. The word intrinsic, what is the meaning of intrinsic is, just because it exists with that property, and that's all. It is not that you created. And it is also a point to be noted is that property you cannot modify it, whether you like it or not. Okay, suppose if you say that I don't like the charged property of electron, I want to make it neutral, you can't do it. Okay, so whether you like it or not, an electron will have charge associated with it, that cannot be changed, and such a property is known as intrinsic property. Extrinsic property means something that you can modify. You can modify something. So what you can modify, for example, you are wearing a shirt, for example, and when you are doing the manufacturing a shirt, you can change its color. If you don't like a particular color, you can change a color, and then you can make your dress, which means that there is some flexibility to you to modify some property. I am talking about color, for example. Okay, you can do so many whatever people are manufacturing, for example, they manufacture to the personal taste or personal interest, or depending on what people like. So when these kind of things come, there are certain properties that you can modify. So if you are able to modify something, and that property is known as extrinsic property. If you cannot modify something, whatever you, whether you like it or not, you can't do anything, then such properties are known as intrinsic property. So therefore, so we are now going back now. So you have a capacitance. How capacitance came is that you have a charge, I have a potential difference. So you can always make the combination with this, whether it is product or ratio that you already know. Then you can generate a capacitor, and that gives you the charge storing device. So if you go back in this direction, that's what I'm talking about. So if you are going back in this direction, how do you got the voltage? Means I have charges that are moving. So if there are one charge is there, second charge is there, third charge is there, this has to move like this. So you have to apply a potential difference between these charges, which means that this is present in a wire. Then automatically these charges are started to move. So therefore, because of the charge only it is moving. So then you ask the question and go back here and then ask where from charge came. Charge exists naturally. That's what I'm trying to say, and that property is known as the intrinsic property. So I am just explaining. It is not that I am asking you to memorize anything. There is nothing to memorize. As people try to understand the nature, they try to do some experiment, and from the experiment they write down their observation in the name of, say, law, a particular law. Say for example, Coulomb law is an example, Newton law is example. Everything is based on experimental observations, and then they try to understand further. And when they try to understand further, you end up in finding some new device, and then automatically you have to describe them with a particular unit, and that is how the new units are coming to picture. Okay, the next one would be the resistance in ohms. Conductance which is not a new one, simply it is in inverse, so there is no new definition. So inverse of resistance. So here I will put a small line here. Now the purpose of the line is to just indicate that the above listed 5 physical quantities are sufficient to describe almost many of the physical parameters or physical principles involved in electromagnetism. So these are the majority of them. There may be one or two which can be once again calculated from these things. So that's why I've written that there are only 5 of them are there. So that's why I already told you that you don't have a very big list, and therefore there is nothing difficult to either understand this. These things come from understanding. You start with the Coulomb's law, then this one comes from the Biot-Savart law or the Ampere's law. Capacitance comes from the only from these two, and the resistance automatically comes because when there is a potential difference and when the current is flowing, you get the resistance, and the inverse of the resistance is conductance. So therefore there is nothing more than what you know in the higher secondary basic ideas, whatever you learned, that is what we are now listing out. And only thing is that I told you that we are going to find the base SI units corresponding to that. So that is what we are going to do. But before that, I don't want to close the eyes and simply write the list and then show you these are the things. Okay. You also need to know how to write them. Not that you look at the sky and memorize all of them. You are not memorizing anything. Okay. Historically, people have discovered something, and then depending on that, certain new things keep on coming, and in the same order we are listing, and therefore it is very easy to understand. So I have put a line here once again. The reason is that up to this you describe with a reference to the electricity. That means you have a charge and the charge is moving and you limit with the current. That's all. The effect of the current you did not go. The effect of the current means what? Because of current something happens, and that is called magnetic field. So that part is not introduced till now. So once you understand that magnetism is coming because of the electrical current, so naturally you have to understand how to measure it, and therefore you need a new unit for that. So that's what I'm going to write down, and that is the magnetic flux. I'll once again tell you certain names are very important. So the terms that I am writing, you try to use the identical terms, because different textbooks will have slightly modified terms, and that gives you more number of confusion. Okay, if you are going to refer to say 3 or 4 books for example, and slightly different terms will exist for describing the same phenomena, when terms are changing you need to understand equivalent meaning. Okay, otherwise what happens is you keep 7 different names, and what do you think is there are 7 different things? It is not so. The different terms that people are using may be referring to the same thing. So that clarity should be there. Otherwise, it appears as if there are too many things are there. So therefore, I am now listing with a particular technical term. So magnetic flux means you try to use the same term without changing it. So this is one thing that you will be measuring in Webers. So whatever I am explaining, it got more relevance or more importance to this particular thing. That is item number G I am writing, and that is the magnetic flux density. This has to be measured, as you already know, it is Weber per meter square, and that is also equal to a Tesla. Okay, this is the derived unit. So we have not gone to the decomposition till now. I am only listing out these things, and therefore the important point once again what I am trying to say is the word magnetic flux density, and here you have a magnetic flux. Now what is the confusion coming here is that many books use an alternate name called magnetic field. But there is a trouble here. Magnetic field has 2 different meanings depending on whether you are going to describe it in material medium or in vacuum. So if you don't want to get any kind of confusion, it is always better to use magnetic flux density if you are going to express in Tesla, because there is another unit is there which we will see later. The units for the magnetic field, for example, is ampere per meter. So this is the unit for magnetic field. It is there, and many textbooks also use magnetic field in Tesla. You should please see this. Unless you open books and see that once you are having 2 different books saying that, one book saying magnetic field in ampere per meter, another book is saying magnetic field in Tesla, then you get confused. Whether Tesla and ampere per meter are equivalent? No. So that's what I am telling. So Tesla is not the same as ampere per meter. If it is not same, how can you use magnetic field for both the place? So such kinds of confusion will come. That is why it is always better to fix a particular term and then use the same term whenever you are describing a physical quantity in terms of Tesla. And wherever a particular name is required, like magnetic field, then the clarity should be explained while writing. Okay, so that point keep in mind whenever we are going to discuss about this flux density. I will explain this point once again when we are going there. Okay, so right now this is the name that you try to keep for the magnetic flux density in terms of the Tesla, rather than magnetic field. I want to say that rather than magnetic field. So this is a preferred terminology. And then E of G, then you have I. The last one required is only in inductance. It is very similar to capacitance. In the case here, you see, in the case of capacitance, you store the electricity. In the case of the inductance, you store the magnetic field. Okay, so magnetic energy is stored here, electrical energy is stored here. So I am trying to say the analogy so that the list will come in a very natural way. So rather than memorizing, the list will come naturally if you put analogs of that. If electricity is stored there, what will be stored in magnetism? Like that, if you ask the question, automatically inductance will come. And then that is going to be measured in Henry, and we are going to see what is the corresponding decomposition, and that's all over. And only 7 of them are there, so that describes almost everything in the case of electromagnetism. If anything extra comes, it can be again modified with these units. So the point that I am trying to tell you is that you have a small number of physical quantities that you have to learn, and that's all. There are only 7 base units are there. There are only how many are there? This is 8 items are there for the case of physical quantity. So now what we will do is we will take an example of the first one, namely the Coulomb, and the second one, volt. So if you can do these two things, you know how easy it is to do the rest of the thing. So we will start with the first one. The first one is, by the way, is so definition we'll see it is straightforward. The first one is straightforward. Okay, we are now seeing the first one, namely the charge to be measured in coulombs. Now the point to be noted is that every time you need to have a defining equation. The defining equation is going to tell you how to decompose the unit into the fundamental units. Therefore, defining equations are something that is very important. Exactly in the last class, you remember that I have written down what is the meaning of 1 coulomb as a definition. Did you remember? We have written a small equation and put a box, and I also explained why a box is put there. Okay, we have not done any calculation, we have not done any derivation, and without that, why did you put a box? I asked you. Okay, the reason is that is the defining equation, which means that equation is the most fundamental one based on which the other things are built up, and therefore that is a very important one. So the defining equation for the Coulomb is what you have to take, and we have seen in the last class that what we have seen means the meaning of definition. What do you mean by 1 coulomb? How do you explain? That definition is what is called defining equation, and we have seen that the coulomb, that is the C that we are going to write down, is equal to ampere multiplied by second. This is what we have seen in the last class. So and therefore what happened to the to the decomposition into the base unit means whether ampere is base unit, whether second is base unit, like that you have to ask the question. Whatever you have written in this equation, ampere here, this particular ampere is already a base unit. You don't have to do anything. Second is already a base unit, which means that this equation is already in the base unit. You don't have to do anything. That is the important point. And if you want to write down in the case of the what you call the in terms of the square bracket like this, you can write down that the dimensions of the charge can be written as like this. You can write the dimensions of the charge is equivalent to, you write down the dimensions here. A is ampere, and you have to remember what is the symbol for the current, capital I you have to write down, and then ampere, the power you have to see. Here there is no to the power, that means there is a 1 here, so there is a power 1. Okay, then you have multiplied by second. Second is time, therefore you write t. So you don't have second power minus 2 per second, nothing is there, and therefore here also you have a 1 here. So 1 will be the power. So I to the power 1, t to the power 1, that's all. This is the answer. This is what I mean to say, that when you are whenever you are trying to decompose and write down in terms of its base unit. The first one I already told you that it is very easy, because that is the place where the definition of the SI system itself started, and therefore this is readily available, so you don't have to do anything. And that's the definition you have, which means that the how do you read? You have to read this particular statement. You have to read like this. There is a square bracket, so you say that the dimensions of the charge is the same as ampere to the power 1 and time to the power 1, or current power 1 time to the power 1. So either you write C equal to AS. This is also fine, there is nothing wrong in this. You can write like this, C equal to AS. But if you want in the form of dimensions, you can put square bracket and write. Both of them are correct. You can writing this is also very much correct, no problem in this. So if you want to write in terms of dimension, write a square bracket but put I. If there is no square bracket, remember that I is not there, A is there. That's what you have to remember. Here S is there, here T is there. So that part you have to take care, whether you are putting square bracket or not putting square bracket. And that's it. So your first thing is over. So what is the second thing that you have written in the previous table? You have to see that after the charge we have written the what you call potential difference to be measured in the volts. So this is not trivial, like it is not readily available. Volt is not there in the list. You have the 7 of them are base unit. In that 7, voltage is not there. So that is not, which means that it's a clear indication that voltage is derived quantity. It is when it is not available in the table, it is one of the 7, automatically it is derived. So you have to now derive and tell me what are the decomposed expression. Now for that you need the defining equation, because defining equation is the starting point. If you don't know that, you can't do anything. So once again we will write down what is the defining equation. So here the interesting point is that the defining equation is the power in an electrical circuit is equal to the product of the voltage and current. So I am now writing all these things because many of the basic definitions and these elementary concepts are already introduced in the school. So I don't have to wait until you move on to the different chapters until you reach the current electricity. Okay, so the basic definitions are very simple, and that is enough for doing this calculation. So let us therefore finish this, and only then we will go to the exact electrostatic problem and then see how the vector calculus is used, because you remember where we have to go. Our electrostatics, first of all we have to start with the vector calculus and write down the Coulomb's law in vector form. But before that I feel that it is more appropriate to explain the SI base units and derived units, and therefore we are doing this. Okay, so P equal to VI, and that you can write down that where P is power. So I can write down that you have to write down the dimensions of watts. P means power, so I am writing watt. Then we need voltage, therefore this has to be divided by the dimensions of the current I. If you do that, then I must be getting the dimensions of the potential difference. I'll write PD. So PD for the potential difference. And this is what you have to simplify. And how do you simplify this? And you know what do you mean by watts? That means the amount of the energy, or you write down that this is joules per second. If you write down joules per second, this is the watts. Then divided by I will be written as the corresponding to I you have A. So you have to write down the ampere as the unit. That's what you have to write. And then again simplify this. So what is joule? Joule is the energy. So energy means Newton into meter. So basic definition you have to use. So the volts can be now decomposed like this. So whether you want to write it in the square bracket notation, that is only a optional one. Then here you have to write down the open a square bracket and then write the V, for example, because this is derived unit, so there is no proper symbol. You can write down square bracket of volts. Then here you write down the square bracket of mass, you have to write length here, etc. And here you put a capital I. That is the only thing that you have to remember. So once you finish this, so this will be the decomposition for the volts in terms of its base unit. So once you have an idea about how this is working, then the rest of the thing is very simple. So what is the third item that you have in the list? The third one is the capacitance. Coming to the defining equation for the capacitance, it is your familiar known equation that the charge on the capacitor is equal to C times V, which means that you write down C is equal to Q by V, and once this is there, then it is a matter of two lines to get the answer. So Q means you already know that is charge. Charge is defined as ampere multiplied by second divided by voltage. So for voltage, just now you got the answer here. This is the equation. I will say that this is the equation number B. Okay, so that is for the voltage. You don't have to do any work now. Directly copy this now. So which means that we can write down that this is kilogram meter square second to the minus 3 ampere to the minus 1. So you get the answer in one line. So that gives you. So what you understand from here is that the doing or decomposition is very simple, provided you know the defining equations. So that is the lesson that you are learning. And once the idea is clear, the rest of the thing is you can do it quickly. I am now explaining slowly, but you can do it quickly once you have the idea about how the things are done. So the next in the list that we have is the resistance, and the equation is a familiar equation to you, which is nothing but V equal to IR. So use this expression that tells you that the dimensions of the resistance will be given by the dimensions of the voltage divided by that of the current. So you have the dimension of voltage in the previous equation. So let us go back. So the equation number B is the expression. So equation number B, this one is what you are going to put in numerator place, and in the denominator there is nothing to do. There is no big, this is a simple A here. You are going to remove the square bracket I and put a capital A for the ampere, and therefore you can straight away write down the answer because there is nothing to simplify. So let me write down this B part here. That means kilogram meter to the power 2 second to the power minus 3, and there is a ampere power minus 1 already here, and there is going to be one more ampere coming down here. Therefore that must be ampere to the power minus 2, and that's all. So that will be the expression for the dimensions of resistance. So we can say that this is equation number D. So for the conductance is actually 1 divided by the resistance. So that is essentially an ohm inverse. That is the definition. So ohm inverse is the definition. So defining equation is simply 1 divided by R. That itself is the defining equation. So you have to now write down whatever is there for the resistance, that you have to write down the corresponding dimensions. So that would be in equation number E. So till now, so let us now go back. So till now, how many of them is completed? 5 of them we have completed. So which means that these 5 of them belong to the electrical part. Okay, or we say that the one which is dealing with electricity. First one, the Coulomb, volts, farad, ohms, and resistance, inverse of the resistance. And what is left out is the remaining 3 of them are left out, the one which is corresponding to the magnetism. So once again, it is not at all difficult, it is very easy, but the defining equations are very important. If you don't know the defining equation, then you do not know how to do this. So now we will start this magnetic flux. Okay, now coming to the case of the magnetic flux, we will write down the defining equation, and you have to think a little bit what equation you can use. And once again, the equation is going to be simple, namely the Faraday's law. And the Faraday's law tells you that the EMF means voltage. You remember that the EMF means voltage generated in a circuit is equal to the rate of change of magnetic flux. So that's what you need. Okay, but in the case of experiment, you observe the negative voltage, therefore you put a minus. But minus is not relevant for defining the case of the dimensions. So you only remember, or you only need to know that the voltage generated in the circuit is equal to the rate of change of the flux. If this equation is there, you can do the calculation easily, which means that. And one more thing here, this derivative will not affect the dimension. You have a time derivative, right? So that point I will explain you. Suppose if you have y is in meter, y equal to, let us say, 4 meter. Let us say y2 is 4 meter, y1 equal to, let us say, 1 meter. What do you mean by all this y1, y2, etc. is, if you have a coordinate system like this is 0, this is 1, and that is 2, etc. Okay, so that is in the y-axis. So what I mean to say by y1 is, this is the point y1. This particular point is the y1. So you can easily understand numbers like this in terms of coordinates. So that is what I am trying to say. Okay, if you have numbers like y1 equal to this, y2 equal to this, and similarly if you have x1 equal to, let us say that this is 2 meter, and if you have x2 is equal to, let us say, 7 meter, for example. Okay, these kind of numbers are there. Then tell me what is y2 minus y1. y2 minus y1 will be 4 minus 1, so that will be 3, but after subtracting, meter will be there. Similarly, if you are going to subtract x2 minus x1, you get 7 minus 2, 5, meter will be there. Now using these things, you divide each one of them. That means you take the ratio between them. Then I'll be getting y2 minus y1 divided by x2 minus x1. So what is that? You get 5 meter divided by, what is y2 minus y1? That number was actually 3 meter divided by 5 meter. So finally what happened? What do you observe now? What you observe is this y2 minus y1 by x2 minus x1, this quantity is what we say dy by dx. So what I am trying to explain to you is, this derivative that you are going to have will not affect the dimensions or will not affect the units. So how is it? Is it visible now? No. Can you check out how it is correct or not? y1, what is the dimension? Meter. y2, what is the dimension? Meter. Okay, what is y2 minus y1? This is again meter. So the difference between them, the dimension and the unit is not changed. And therefore, dy, this quantity, dy, the dimensions of dy is the same as dimensions of y itself. So therefore, the differentiation process will not affect the dimension. And similarly, whatever is said is true for x also. So dx, because of differentiation, dx will not change, the dimension will not change. So what is the dimensions of dx now? It is there here, meter is written. And what is the original dimension of x? Meter is there. So therefore, x also having the dimension meter, dx also having the, here it is, this is the dx. This is the dx. So dx is also having the dimension of meter. So this point is important because now there is a d phi by dt, so you should not worry what will happen if there is a derivative. Okay, that is the point I am explaining. So I will erase this part now. Okay, so that is what you have, and therefore the dimensions of d phi can be written as dimensions of the electric potential. You remember, electric potential means voltage, and then multiplied by the dimensions of dt. And minus is not required, that's why I have removed it. Minus will not affect the dimension, so no need to write that, which means that since we are going to measure the dimensions in the units of Weber, so we write that this is the Weber, the dimensions of this quantity will be equal to. So now you have to take what is the dimensions of the volt, which we have done in the previous board. So you have to go back in your page, if you have the class notes you will be having, and then you write down what is the dimensions for this particular thing. And remember once again that this is volts, which you have derived, and that is nothing but this kilogram meter square second to the minus 3 ampere to the minus 1, and this is what you have it for the case of the voltage, then multiplied by dt. So what is dt means? You know what is that? It's a time, right? So you simply put a second here, and that's all. So this gives you, this is kilogram meter to the minus 2. So this second will simplify, we get a minus 2 ampere to the power minus 1. On the left side you have the Weber, and that is the required result, which means that Weber, which is a derived quantity, is expressed in terms of the base SI units. That's what we have done. So let us say that this is your equation number F. The next one will be the magnetic flux density. So I will write down that. So the defining equation for the magnetic flux density is magnetic flux divided by, or we say per magnetic flux per unit area. So magnetic flux per unit area is what is called the magnetic flux density, and we will say that this is in equivalently written as Weber per meter square. So that tells you that the magnetic flux density is written as, let us say that this quantity is Tesla. So maybe I will write in, I think we are writing in white color, right? So let me go back to the white color and write down. So that gives you, so what is the dimensions of the Weber that you have already, and there is a divided by meter square. So directly you can write down that this is a kilogram. So this is meter to the power now minus 4, because 2 here and 2 here, the remaining things are same. I will write second to the power of minus 2 ampere to the power of minus 1, and that will be equivalent to Tesla. And then we are left out with only one quantity, last quantity, namely the inductance. Once again, the defining equation you have to think. Of course, these things are known to you, basic definition. Okay, what is meant by inductance you have studied. So I will explain, I will tell you what is the meaning of inductance, and that will help you to write down the equation. So it is like this. In a particular circuit, circuit means simply you have a battery for having a voltage or potential difference, and then if you are having some kind of resistance in the circuit, then automatically current is going to flow. So certainly there is a voltage, there is a current in the circuit. That's all. There is nothing more complicated than that. So the defining equation for the inductance is once again simple. It is the voltage generated in a circuit per change in the current. That means you are going to change the current in the circuit. The change in the current is what is written as dI by dt. So the appearance of the equation, you should not think that it is complicated. It is not complicated. There is a current flowing in a circuit. You change it. Uniform current should not be there. That is the meaning. If steady current is flowing into the circuit, you change the current slightly so that the steady value changes to a new value. When there is a change in current in the circuit, there is a voltage developed in the circuit which you are measuring. So the question is, how much voltage is developed in the circuit because of your change in the current? You are going to do this measurement. If you do the measurement, you get a number. We call that number as the inductance. That's all about it. So everything you are measuring the current, you are measuring the time in a stop clock, and then you are measuring the voltage that changes, or the voltage that appears in the circuit because of the change in the current. If you do that, if you calculate this quantity, all these things we divided by dI by dt, and that is what we are going to call this as an inductance. And so we will write that. So once you have this defining equation, it's very clear that all the items are known quantities. So what do I mean by that? What about the volt? You already have the expression for the volt. You copy that from your what we have done in the previous board. I think the expression for the volt is something like kilogram. You verify this. It looks like this, something like kilogram meter square second to the minus 3. So finally you get this. This is ampere per second from here. So there is nothing to do. This voltage is already available with us. So you have to take it from there and then simplify this expression. I think this second will go up here. That's why minus 2, and other things are fine. So till now what we have done is we have seen that there are 7 base SI units, and then we need 8 of the derived quantities in electromagnetism. They are the one which are most frequently used. If anything is required, you can always generate them from these things. And you have learned how to convert the derived physical quantities in terms of base SI units. And you have seen that nothing is complicated here. Hardly you have to do 2 3 steps for the calculation. And the most important thing to remember here is that the defining equation is the most important thing. You should know how a particular physical quantity is defined, and therefore remember that the definition is very very important. If the defining equation is not known to you, you can't do this particular decomposition. Okay, after having discussed the SI base units and the derived units, and in particular how to express these electromagnetic units in terms of the base units, let us now make some concluding remarks on the Coulomb's law so that we can conclude this particular lecture. What I am trying to say is that we have made a statement in the previous lectures that the constant k can have dimensions or it may not have dimensions based on the system of units that we are going to choose. So regarding that, we will make one conclusion. The second point is, I also told you that we are going to explain or we are going to make a mention about why the 1 divided by 4 pi epsilon naught is present and where from the 4 pi is coming into picture. That is one thing. And the second thing is a small remark on the epsilon 0 itself. So these are some of the points that we will see so that we can make a conclusion on this particular lecture. So the first thing that we will see is by writing down this equation once again, namely F is equal to K into Q1 Q2 divided by R square. From here what we have done is that if you are going to express this in the CGS system, let me write down quickly that this will be dyne multiplied by, you have a centimeter square, and then here you will be having the stat coulomb, and therefore that will be equal to the stat coulomb square. So that gives you the dimensions of the stat coulomb in the CGS system is equal to, you have the dyne to the power of half multiplied by the centimeter. So this one, if you are going to express further, what is meant by dyne you already know that it is 1 gram of the material should be accelerated by 1 centimeter per second square. That is the meaning. So you simplify with this power 1 by 2 and multiplied by centimeter. So that gives you gram to the power half, centimeter to the power of 3 by 2, and second to the power of minus 2. So that gives you the dimensions of the stat coulomb. So why do you want this is that I am just writing whatever we have done in the last class, and we made this particular as one of the main results in the last class. So this is the situation in the case of the CGS system. I am writing this because we are going to make a direct comparison with the SI system. So in the SI system, we have the coulomb instead of the stat coulomb. And on the right side, we don't have this kind of to the power 1 by 2, 3 by 2, etc. We don't have anything. Just 10 minutes back, we have seen what is the definition for the coulomb. Namely, it is ampere multiplied by second. So there are no power half, power 3 by 2, even seconds is not to the power minus 2. So you can now see the contrast. So in order to make this contrast visible to you, I am writing both of them together. So this is our main conclusion, that it is the charge in the SI system. So you can see that when we are making a transition from the Gaussian CGS system to the modern SI system, there is a lot of changes there in the case of dimensions. So this is the first point, very important point that you have to remember. And because of this reason, the changing of the dimensions or units from one to the other requires a little bit of work. It is not as trivial as in the case of mechanics. So this is the first remark and the first important point that I would like to tell. So this is regarding the dimensions of the charge itself. This is the first point. The second point is about the dimensions of the K. So the second point is about the, so regarding the, or we'll say that about K, for example. So what are the dimensions of K? That this also we have seen in the last class. So let me write down how do you write this. So the dimensions of K we can write like this. K will be of the form, or it can, we can write down equal to also, not a problem. But this can be expressed as, so let us multiply these two. We will write that this is dyne. Then you have a centimeter square. Then you have divided by stat Coulomb square. But however, these each one of them will cancel if you are going to substitute this. You have to understand what I am trying to say. If you are going to take this stat Coulomb here, and then you bring this and substitute here in this particular place, everything will get cancelled, and therefore it will have no units. So I'll that's what I'm going to write down, that this will be having no dimensions in the case of CGS. So that I will write in the bracket. So this conclusion you already know in the last class, but now we are making remark. So how it becomes dimensionless? That is straightforward. We can take it. You take this one and directly substitute. It is a matter of one line. You have to cancel everything and then show that this is dimensionless. So that's clear. So next, what I am trying to say is that if you are coming to the SI system, so it is once again it is about the K only. So once again this is about the K in the SI system. And we are going to make a conclusion about what is the dimension of K. In the last class, we have not discussed. Remember this, in the last class, we have not discussed the dimensions of K in the SI system. So that we are making freshly now. So which means that we are going back to the same equation. By the way, equation will not change. So I'll put the equation here. This particular equation will not change from whichever unit that you are going to consider. Same equation, but let us write down what is the dimension of K in the case of the SI system. So let us write down that the dimensions of K will be looking like, it is the dimension of force, which means that it is Newton. Then here you have a meter square by cross multiplication, and then this Q1 Q2 you take it to the denominator. Therefore I must get the Coulomb square. That means the dimensions of K will be Newton meter square per Coulomb square. That's fine, but this is not base unit. There is nothing wrong in writing this. You can always say that the dimension of K is given by Newton meter square per Coulomb square. It's good and it's correct. But however, since we are now learning how to rewrite the same expression in terms of the base units, let us exercise one more step further so that you know how to convert this to the base SI system. So Newton is the force that you know. What do you mean by Newton? It is 1 kilogram of the substance, or that you have to accelerate by 1 meter per second square acceleration. If you do that, that is called 1 Newton. So that is what is written here. Then multiplied by, you have a meter square, then there is a divided by, and what is Coulomb? Coulomb is ampere multiplied by second. Then you have a square. And that's all you have to do. And now let us simplify this. That gives you, this is kilogram. Then you have a meter and a meter. So let me write down that this is meter cube. Then here you get a second to the minus 2, but there is a second to the plus 2 in the denominator. I think that will give you second to the power of minus 4. And finally you have ampere to the power of minus 2. I think it's correct, right? You can verify. So 1 kilogram is here. Yeah, that's correct. Meter to the power 3 and so on. And that's all. We have completed this. So let us write down that this is the dimension of K. And for contrasting result, I will put a highlight here. So this is our one of the main conclusions that I wanted to tell you, that when you are making a transition from the CGS system, so remember that this is CGS. From the CGS system, if you are going to make a transition, you see how the dimensions of K is changing. So the dimensions of K in the base unit can be expressed like this, and this is one important result. Okay, so two main conclusions are the remarks that we have made, and let us make one more small remark so that we can make this lecture as a complete one. The third remark that I am going to, or I would like to tell you, is that it is regarding the 4 pi. You should remember that in the case of the SI system, we have the expression K is equal to 1 divided by 4 pi epsilon naught. So in this expression, this 4 pi, where from it is coming? That's what is the point. Now usually where from it comes is, basically it comes from spherical coordinate system. Now you should remember one thing, that when you are discussing certain things having spherical symmetry means what? Suppose if you have a light bulb and you switch on the light bulb, in which directions the light will go means it will go all the 360 directions in the front side. It also goes on the top, it goes to the bottom, it also goes on the back side. In all the direction, remember 360 is just what you call only in planar direction. That means in one plane it is 360. In the front also you have 360, in the top there also you have 360, like that several of the 360s are there. But 360 is one of the simple way of telling, or in a plain English you can tell, but this is not correct technically. 360 is a planar angle, and that is what is the meaning of 4 pi now. So 4 pi is actually the technical term corresponding to the colloquial word 360 degree. So you should remember what I am trying to say. Suppose somebody says you have to be very careful, keep looking all the 360 degrees around you so that you will be safe. Like that, if someone tells to you, what is the meaning? 360 degree doesn't mean that you have to look only in a circle. So remember, if you are going to make a circle like this, and then starting from any point, from this particular point P, you travel like this, 360 degree if you make, you will come back to the original point. That is not the meaning in that sentence that I said you. All the 360 degree you keep an eye, so that you will be very much alert and be safe. Like that, if someone tells the meaning of 360 is not this, that is not the meaning. The meaning is you have to keep looking in the front side, in the top, that is you have to see above and look at the sky and see if there is any trouble coming to you, and also you see on the left side, right side, and also turn back and see, and also see down also. That is the meaning. So which means that the technically, how will you tell this? This is only the colloquial language 360. So technical term for this kind of explanation that I said is the 4 pi steradians. So steradian is the unit for, now remember what is it? Radian, you know. So this is actually radian. This is 2 pi. You have the radian. 2 pi radian is basically 360 degree. That is what people say, 360 degree. Now you can't say 2 pi because it is on a plane only. This is on a plane. You have to come outside the plane to make a sphere. Circle means what? It is a two-dimensional object. You have to come out of the plane in order to make a sphere. So when you do that, this 2 pi radian has to be found out, or we have to find out how many steradians are there. Now you can't use radian. Radian is the unit of measure only in the plane. If you are not in the plane, if you are in the three-dimensional sphere, then the corresponding unit will be steradian. Simply one STE is there. See, STE will be added to the radian. So that is the steradian. And this is for the 3D. And this particular normal radian is for the two-dimensional situation. So this 4 pi basically comes by doing the integration. So let us not go into the integration right now. Anyway, when you learn the spherical coordinate system, this integration can be done easily, not a difficult one. So therefore, this the meaning of this particular statement is can be reframed in a technical language like this. You keep looking in all the 4 pi steradians and you be alert. That's what you have to tell. If you are going to use technical term, this is what you have to tell. Keep looking all the 4 pi steradians around you. That means if you are looking in all possible directions, whether it is left side, right side, down, up, or the back side or front side, or any other angle, if you are going to count everything, and that is called 4 pi. Okay, so everything around you is called 4 pi. So your eye has to go through all the places around the sphere. If you do that, we say that you have covered all the 4 pi steradians around you. That is the meaning. So because of the spherical polar coordinate system that we are going to use, this 4 pi has entered into picture. So this is the one particular note on how this 4 pi has entered into this particular expression. And the last comment that I would like to make on this is about the epsilon 0. So this epsilon 0 basically came only after the Maxwell's discovery, saying that what is the Maxwell discovery? Maxwell has discovered that electricity and magnetism are not separate phenomena. Electricity and magnetism are related to each other. That is first point. Second important point that Maxwell has discovered is not only that electricity and magnetism are related, but this electromagnetic information will travel at the speed of light. This is the most important conclusion that Maxwell has done in about say 1860. So roughly about 1860, Maxwell has given this very important, and it's one of the one of the most important conclusions in the history of science that make a big revolution. So you should remember that the statement means that the electricity phenomena plus magnetism phenomena plus any optical phenomena, all these phenomena, they come under one roof. Come under one roof means it is, we say that it is one branch of study. So you don't have to say that electricity is separate, magnetism is separate, and optics is something different. We will study optics in the fourth semester. It is not like that. Electricity, magnetism, optics all will go together. So under the single name called electromagnetic theory, that is what Maxwell has given. So it is, and therefore this epsilon 0, by the way, has a connection to the speed of light. That is what I am going to tell you now. Now before that, I want to tell you, because of this reason, this Maxwell's contribution is very important contribution, giving the important unification of physical laws. Or you say that we are going to say unified theory. If you are not going to, we are not going to tell specifically anything about a particular law. So instead of saying a physical law, I can say that it is a unification of physics, or we say that it is a unified theory. FIED. So what is unified theory? The electromagnetic theory, I'll write here EM theory. Electromagnetic theory is a unified theory. Why it is called unified? The term unified you may be familiar, because generally in the higher secondary school, when you are studying, maybe somebody might have given some encouraging lectures and speech saying the unification of forces, the so-called grand unified theory. People, I mean the scientists, are working towards the discovery of unified field theory. What is the meaning of unification is that we want to understand whatever is there around you, We don't want to say that that is mechanics and this is optics and something else is a different study which you do not know. It is not like that. It's not scattered, but we want to bring everything under one roof. Everything under one roof means you learn everything or you understand everything in terms of some phenomena or in terms of some underlying concept. If that happens, then we say unification is taking place. If that doesn't happen, then they are all scattered. Unification is not that, scattered. Everything is scattered. You will be having 200 equations and some 400 laws, and you will not be able to understand what is the link between one law and the another principle. So it will be too much scattered, and then that leads to difficulties in understanding and grasping the entire thing. That is the point. So the point why unification is very important is whenever you unify certain things, that means bringing into a common umbrella, then understanding the theory is comfortable, it is easy, and therefore you can make further progress in the science. So therefore, the most important contribution of the Maxwell is the unification of electricity, magnetism, and optics. This is the second unified theory. And where is the first unified theory? The first unified theory is given by the Newton. So that also you should know, because you have already completed mechanics, so you may be knowing this. The first unified theory, the first unified theory is the mechanics by Newton. So what is the unification is the three laws of mechanics, namely first, second, and third law. That is one thing. In addition to that, he has also made one more thing called Newton's gravitational law. So everything is coming under one head, okay, namely gravitation. So that gives you some kind of unification. So there is a big unification on the mechanics side, and there is a big unification in the electromagnetism. But people are now searching for further unification in terms of other branches of science, like for example quantum mechanics, relativistic quantum mechanics, or theory of relativity. So such kind of things has to be unified. Still they are lying separately. So people are now searching how to unify all these things together. It is not successful till today. So great scientists are working in this particular area, and if someone discovers, then that will be called grand unified theory. So people are working on that. So you should know that this is one of the important discoveries and important contribution by the Maxwell, that the electromagnetic theory is the second unified theory. Okay, coming to the epsilon zero itself, the point is that, see, epsilon zero is the quantity which comes in the constant of the Coulomb's law, and you take another constant that appears on the Biot-Savart law, because Biot-Savart law deals with the magnetism and the Coulomb's law deals with the electricity, namely electric field. So electric and magnetic field, these are the two things that happens. If you take the product of these two numbers, it so happens that this is exactly equal to 1 divided by c square, where c is the speed of light. So it is a real surprise. I am doing an experiment with electric charge. Either the electric charge is stationary, that means it is at one place, it is the charge is at one place like this q, or that I have a set of charges that are moving in a wire, like this in a wire, it is moving. So that creates me a current I. Now the question is, when I am doing an experiment with a single charge or several of the charges, for example, I have several of the charges, they are stationary. This is one experiment. In the second experiment, I am passing a current I in the wire and I am measuring the magnetic field. That is what I am doing. But the question is, this mathematics says that you get 1 divided by c square. So that means velocity of light is coming into picture. So immediately you ask the question, what is the business of light here? We did not invite light. We are doing experiment with the electric charge, and we are doing experiment with moving electric charge. We didn't invite light here, and we don't do any experiment with the light. So then if it is the case, then why there is a 1 divided by c square coming into picture? And therefore this question has given a think over, that is, you have to think over. Then Maxwell gave a conclusion that the electricity and magnetism are related in such a way, and in what way it is related, that's what he is giving. The electricity and magnetism is related in such a way that the electromagnetic information called the electromagnetic waves, they travel at the speed of light. So he gave the connection how electricity and magnetism is connected to the speed of light. Light means it doesn't mean that it should be visible. That is very important. Electromagnetic theory clearly gave an evidence that it need not be visible light. Invisible light is also light only. It can be infrared, it can be ultraviolet, it can also be gamma ray. Everything is electromagnetic waves. So, irrespective of optics means by optics we mean that we are restricting ourselves only to the visible radiation. Invisible radiation you don't study under the optics. But this electromagnetic theory by the Maxwell tells that, or he says that, you don't have to restrict yourself with optics alone. You can start anywhere from the ultraviolet to the infrared and go all the way up to the gamma ray. Everything comes under one umbrella, and everything will travel with the speed of light in vacuum. Now, that vacuum is the reason for the zero. So, there is a zero here, and the suffix. What is the meaning of the zero in the suffix is that we are doing the experiments in vacuum. Another name for vacuum is the free space. So whether you say free space or whether you say vacuum, both refer to the same thing. So only in the vacuum you have this expression. If it is not vacuum, then additional small constants will enter into picture. That right now we will not worry. So the point is very clear now how the epsilon zero is coming into picture in the SI system, because after the understanding that electromagnetism is not an isolated study, and it is related with the speed of light, this particular expression has come, and therefore people have fixed this 1 divided by 4 pi epsilon naught as a suitable constant that can appear in the Coulomb's law. And anyway, this will automatically, this particular constant, whatever constant I'm going to talk, this particular constant will have the dimensions that we have mentioned. It is a, so those two are in agreement. It is not that they are isolated. So here, so this is what I'm trying to say. So whatever this particular k that I have, it will have the dimensions of this. Because this is in SI unit, remember that this particular expression 1 divided by 4 pi epsilon is valid only in the SI system. So therefore, it will have this dimension. There is no question about going to the left side here. No dimension, because when it is no dimensions, there is no 1 by 4 pi epsilon 0. It is just k equal to 1 without any dimension. So that trouble will not come. So this is the these are some of the important points that I would like to tell about this Coulomb's law. Okay, so with this we will stop now. We will see in the next class how to understand the direction of force in the Coulomb's law, and then because of that reason we will also see how to write the Coulomb's law in the vector form. That we will see in the next class.